Okay, let's continue. So we have been looking at switch capacitor circuits. So we basically started off with this simple switch capacitor amplifier. So we saw it a couple of times. So in clock phase phi 1 we sample the input across this capacitor C, and in the other clock phase we transfer this charge to the capacitor CF. So we transfer a charge of C times V in to the capacitor. So the output voltage is C by CF times V in, and we also recognize that there is half clock cycle of delay from the point you sample the input on C to the point the output is finally available at the output. Okay, and then we saw if we don't want to have this delay, we decided to do both these operations in the same clock cycle. That gave rise to this modification. So here we are sampling the input and transferring the charge to CF in the same clock phase. So here there is no delay, and here the charge that we are transferring here is C times V in. So the charge on this plate is plus C times V in. So if you find the output, what is the output here? I mean, output is basically what is the charge on this plate? Minus C V in. So output voltage is fine. So basically just be comfortable with this, because I mean next time when you see this, you should be able to recognize and say which one is delayed, which one is delay free, and what is the sign, whether the gain is positive, negative, and so on. Okay, cool. And in the last class we also saw how to solve these circuits using charge conservation. We saw a bunch of examples. We saw how to calculate the transfer function it realizes in discrete time and so on. So in this class we look at how to make circuits that realize a given transfer function, in particular only those relevant transfer functions in ADC applications. Okay. And for that, first let's look at how to realize one important block in circuits, which is an integrator, because as you will see going forward, integrator is one crucial and most powerful block that will be used to make lot of circuits, true in signal processing also. And in continuous time, you guys know the deal. If you have a signal something like this, if you want to find the integrated output, you just take the area under this curve. So y of t is, if I write it, let's say from 0 to t, x of t dt. So what is the transfer function here, h of s? If I take y of s by x of s, 1 by s, this I hopefully everyone is comfortable with. So how do you implement this in continuous time? If you want to have an integrator, have you guys seen a continuous time integrator? Yeah, again the observation starts from the fact that I need something of the form 1 by s. If I look at a capacitor, its impedance is 1 by s. See, that's because if I look at the capacitor voltage, how is it related to the capacitor current? If I know the capacitor current, how will I find the capacitor voltage? 1 by C? So this is a fundamental relation, so we try to exploit this to make an integrator, right? So if you have any input voltage and you convert to an equivalent current, make it flow through a capacitor, the output will obviously be an integrated version of the current. So this is what we use, right? And to exploit this, one way to build the circuit is this: you take the input, pass it through a resistor, and then you give it to the virtual ground, something like this. So here the current is forced as V in by R. That current is made to flow through the capacitor so that the voltage is obtained as the integration. This is something I'm sure everyone knows. But one thing to have in mind is an integrator is never used in open loop as such in any place. Okay? Like, there are a lot of reasons. One reason is, in practice, whenever you make an op-amp, the op-amp needs to have negative feedback at all frequencies, including DC. Only then the DC operating point, bias points will all be set properly. So now if you use it like this, what can you say about the capacitor at DC? Capacitor is like open, so there is no feedback at DC. So operating points won't be set properly. And otherwise also, let us say we are using it like this, and let us say the op amp has a small DC offset, or let us say the input has a small DC. If the input has a DC, what will happen to the output? What is this? I mean, what is this block doing? It is taking the input and integrating. If the input has DC, what happens? Integration of a constant signal is ramp. Depending on the sign, it either goes up or down. So it will eventually saturate to one of the supply rails. Again, it's happening because see here, what is the gain of this block at DC? Yeah, correct. But what I'm saying is, assume that the op amp is fine. Let's say it's an ideal op amp, it's working fine. Then this is 0. Then you still have a current flowing. That's going to integrate.
In every cycle, we have a current going into the capacitor.
Correct. It is like you are pushing a current into a capacitor, right? Here you cannot say that current flow through the capacitor is 0. See, current flowing through the capacitor in steady state is 0, provided voltages are all within limits. If you're driving it with a fixed voltage source, you can be kind of sure that it's fine. But here it is actually converting this voltage to a current. So as though you are driving a particular current. This is happening again because what is the gain of this block at DC? Infinite. And I mean, any block which has infinite gain is actually useless in open loop. Right? You want infinite gain. Why do you want infinite gain? Yeah, virtual ground, but to do what? I mean, what's the point of having an infinite gain if I can't use it? Yeah, basically it is all needed to have a negative feedback loop. Okay, so you will never find integrators like this, happily sitting in open loop. It will all be part of a bigger system which is realizing some kind of a negative feedback loop. So this will ensure that there is also negative feedback at DC. So in practice, the op amps will also be fine. Something to have in mind. Okay. So this is all in continuous time. Now let's.
Open loop only at DC, right? Rest of the frequencies it's in negative feedback.
No, I mean, if you make this, even at DC there is negative feedback, right?
No, exclude the blue one.
Okay, the white one.
The
white one, at other frequencies it is there, true.
Yeah,
it is there. That's what. If it's an ideal op amp, it is okay. Bias points are not a problem. Cool. So let's now repeat the same in discrete time. So in discrete time, I no longer have a continuous envelope like this. I have something. So here, if I were to mimic this integration operation, what should I do? Let's say this is x of n. What does integration mean in discrete time? You basically have to sum up. Let us say I'm interested in output here. So there are two kind of summations you can do. One is where you can sum up till the previous sample. That is, if you are interested in finding the output, let us say at this time instant, you could either sum up till the previous sample or you can include the current input sample also. This kind of gives you two variations. So if I look at the yellow one, what is the expression for y of n in terms of x? How am I getting the output at a given time instant? Summation of, let's say it's x of k, from what values of k? 0 to? I'm summing up till the previous. So which means if I write n minus 1, this will be n minus 2 x of k. So what is the difference now? So you might have seen somewhere, but yeah, what is the difference? X of n minus 1. Okay. So this gives the difference equation here. The output at a given time instant is whatever I had earlier and the input sample. That's basically integration, right? You keep adding things to the existing result. Now similarly, if I were to write the difference equation for this variation, wherein I obtain the output by summing up the current input also. How will this change?
Should be extend just.
Now I am no longer summing up till x of n minus 1 till x of n. The same thing again you can do this. This upper term will become n. Here it will be n minus 1, and then do the same thing, you will get this. So there are these are two different variations we can have. So let's actually write it separately and look at it. So y of n is, this is the first variant. Okay. Second variant is this. Okay. So if I try to find the transfer function h of z here, what will I get? Z inverse by, okay, you just take this here, this will give you z inverse 1 minus z inverse. So this is what we typically call as delayed integrator. Yes, yeah. Okay. I mean, what I'm saying is, this part is okay. What I'm saying is, you can have a different variation of the integration wherein you sum up till the current sample also. So this is one variation where you stop till the previous input. Here you sum up till the current input. That's all. So here, what will be h of z then? 1 by 1 minus z. So this, as usual, we call as delay free. So now let's see how we can make something that can implement this transfer function. So again, let's split up the tasks we have. First, we have to store the output and then keep adding the input to this stored output. So how do I store the output voltage? Capacitor. But it's not enough if I just have a capacitor and store it. I should also be able to process this stored voltage without drawing any charge from the capacitor. So what should you do here? We saw this in the switch capacitor amplifier. To make sure that we don't lose any charge from the capacitor, we take the help of the op amp. Put it like this. Let me redraw it slightly small. Okay. So now we have established this portion. The next portion is trivial. We just have to sample the input and then add it to this. So we use the same old sampling network that we have been looking at. So you sample it in, let's say, one clock phase. You transfer it in the other clock phase. And the output finally you sample at the end of the clock phase phi 1. So this is one circuit I asked you to find the transfer function for. So if you had calculated it, you should have gotten this as the result. If you didn't get it, you can meet at the end and we'll see. Okay. Yeah, this is called a C. Cool. So now we have made this. Now let's see how we can make this fellow. So here the point to notice, we have this delay of Z inverse, because if I look at the timing, let's say this is clock phase 1, 2, 1, 2 and so on. I am sampling the input at this point, end of clock phase phi 1. This is getting transferred to the capacitor CF here, and the output is finally available here. So you totally have one clock cycle. That basically is the Z inverse you have in the numerator. Now in this variant, what we want is, we don't want this delay. So we should not be doing the 3 operations and 3 different clock phases. Instead, same thing as before, we combine everything in one shot, which means I will sample the input, transfer it to the integrating capacitor in the same phase, and then in the same phase I sample the output. There should not be any delay in this, so that's why we do this. So which means in the other phase I go and reset this one. Okay. So again, this is other circuit I asked you to find the transfer function. So if you calculated it correctly, you should have gotten actually minus C by Cf. Again, the inverting sign here is because of the same reason we looked at the amplifier. So here we are directly transferring the charge here. So the charge on this plate will be plus CV in, which means the charge on this plate will be minus CV in. So that brings out the negative sign. So please make sure, you get comfortable with these. So next time if you see this, you should be able to recognize that this is an integrator, delay free or delayed, whether the sign is positive, negative, blah blah. And again, if you look at the continuous time integrator also, so here what we did, we took the input voltage, converted to a current, and made the current flow through the capacitor, and the integration is happening because the fundamental IV relation for a capacitor is through an integrator. So here if you look at it, similar thing is happening. We are actually converting the voltage to a charge in the capacitor and then transferring this charge to CF. So instead of having a steady flow of current, we are actually taking one charge packet, transferring it. That way we are ensuring that we have a current that is being pushed into the capacitor. So same thing here also, we are relying on the fact that the current voltage relation for a capacitor is an integration relation. Cool. So now if you have done this, if you are okay with this, let's look at something. Now let us say I want to realize a transfer function that looks like this. So again, let's try to break things one by one. So first let's see how we can make this. We know how to make this, so I'll maybe copy paste it to save time. So this is basically one integrator. Okay. And we know if I take the output of this integrator at the end of the clock phase phi 1, that gives me the delay portion, Z inverse by 1 minus Z inverse. So how can I get this portion then? This gives me Z inverse by 1 minus Z inverse. I want squared of this transfer function. It's basically cascading. Is that clear? Yes. So I'll basically take this again, paste it here, then delete the V in. So if I call this VO1 and let's say this as VO2, if I sample VO1 at the end of phi 1, I get this part. If I sample VO2 at the end of phi 1, I will get the second part. Till this it's okay. Now let's look at the next detail. Let's say here I choose all capacitors to be same. Okay, so we're exactly realizing Z inverse by 1 minus Z inverse and squared of this transfer function. Now I want to scale VO1 by K1. So how do you think I can, impart a scaling factor to this? Okay, let's say, yeah, that is true. What he's suggesting is you make it K1 times C. But let's say I don't want to do that because that will kind of affect the rest of the cascade. Let's say I do this. I keep equal capacitors in the integrator. Now I want to take this voltage, multiply it by a gain K1. What circuit do you think that can do this? Huh? the switch capacitor amplifier you saw, and we saw two variants, right? One was delay free, one had half clock cycle of delay. Which of the two do you think I can use? Yeah, you can use delay free, but when you use delay free, what happens to the sign? The gain of the sign of the gain is inverted. So you can actually use delay free and you'll have an inverted thing. But also you can use the delayed one also, because if you actually see, this is the clock phase again. So we are sampling the input here, let us say, integrating it here, and then the output finally, if I sample at this clock phase, I get Z inverse by 1 minus Z inverse. Now if I sample and amplify in the same phase, that is the delay free amplification, that gives an inverted sign, right? But if I want to use a delayed amplifier, there I'll have half clock cycle of delay. So there what I should do, I'll be sampling in this phase, because remember integration is happening in this phase. If I can sample the signal at the end of this clock phase and then amplify it here, I get the same effect. Is that clear? I mean, in the delayed free amplifier, what we did was this. What we might be doing is this. I'll repeat it again. So the first integrator is sampling the input at the end of this clock phase. Integration is done at the end of this clock phase. So we'll sample the output in this clock phase. Now if you want to add a gain, we have to do this delayed free amplification in this clock phase. You sample in this, also amplify in the same phase. Now if I want to use a delayed amplifier, I know there is half clock cycle of delay. So I should be sampling at this point. And I can nicely do it because integration is over here. If I sample here and then amplify it in the next phase, that is still okay. Is that fine? So that I'll do that. So if I do this, I'll have VO1. I'll sample in the clock phase phi 2, amplify it in the clock phase phi 1. And this was the amplifier we saw. Amplified in phi 1 and you reset in phi 2. If I call this as some C naught, what should be the value of this capacitor? I want a output K1 VO1. So what should be this capacitor? C naught by K1 or C naught times K1? Remember, the gain is basically ratio of this by this. Okay. So this should be K1 times C naught. I'll write it here. Okay. So now if I this part is done, so I'll get K1 times VO1. Till this it is fine.
C naught times C naught by this capacitor.
No, the gain is the C by CF. Okay. I mean, think of it like this: if you have a resistor, it is the feedback by the input. For a capacitor, it is the impedance. So it's 1 by SCF by 1 by SC in. That way it can be.
The reason for sampling at the end of clock phase 2 was to have superimposition, right?
Not superimposition. You can do either.
We wanted K1 Z1. Right?
Correct.
So in order to have that phase sample at clock phase, right?
Correct. I mean, you can, like I told, you can also do it using the delay-free amplifier by sampling and amplifying in this clock phase. But there you will get the sign to be minus. You can do both. I'm not saying this is the only way, right? You can use both as an answer finally. Cool. So this part is done. Now I also need to scale the second output by K2 and add it to my existing output. How do you propose we can do that now? So first of all, here I am getting K1 times VO1 because I am transferring a charge. What is the charge I am transferring here? K1 C naught times V01 is the charge I am transferring. So the voltage is K1 C, whatever, K1 C naught V01 by C naught becomes the voltage. Now I want an additional term K2 VO2. So what should be the charge I should be transferring to this capacitor? Plus K2 VO2 times. If I transfer this charge, then the voltage will be this. So how do I transfer a charge of this quantity? Where I should add a capacitor in parallel? See here. Huh? Add a branch? From VO2. Let us say VO2 is here. Okay, what do you want me to do? Yeah, so what he's suggesting is, see here we are using this branch to sample a charge of K1 times VO1 times C naught and pushing it into CF. If I want to sample K2 times VO2, sorry, whatever, right? If you want to get a charge of K2 VO2 times C, you should have something like this. This is K2 times C naught. Now this is sampled VO2 and has acquired a charge K2 C naught times VO2. Now the next job is to transfer this in the clockwise phi 1. What do I do to this terminal? Basically go on. So now this branch is transferring charge proportional to K1 VO1. The top branch is transferring a charge proportional to K2 times VO2. So the charges add up like this, and the final voltage is this. Clear? Good. Again, if you just look at the circuit, it might look kind of big, might not make any sense. But the moment you understand what each of these building blocks are doing, you should be able to write the transfer function just by inspection. And you should also be comfortable in the timings here, so that the exact Z inverse, whatever you can take. Is that fine? Cool. So if this is clear, you can try this as an exercise. I gave it as a practice set also. So try to realize a circuit that implements this transfer function. This is in a practice set also. I'm just rewriting. Basically the integrator and feedback. You guys know how to make this? You should be able to do it. Again, you take it step by step. I would suggest you first assume that there is no feedback. Okay. Assume that there is some other signal Vx. Now the problem is a bit simpler. I need to subtract the two and then integrate it. So two signals need to be integrated, one with negative sign, one with positive sign. That's all. And then you recognize that my Vx is same as Vout. Again, you first you calculate the transfer function of this h of z. You make a circuit that you think realizes this transfer function. Solve for the circuit using charge conservation, and make sure that the transfer function you calculate from this block diagram is what you get in your circuit also. Again, there are like 3-4 ways in which you can do this. So if you do it and you got this, you let me know. I can let you know. Cool. So